Aí, calma, só tá iniciando a gravação. É só porque o time. Aí, pode começar.
All right, good morning to everybody. Today I decided to talk a little bit about some mathematics in quantum mechanics. My goal here for today is that I want to present some problems, and when I say problems, I put some quotation marks because there are not exactly problems with quantum mechanics as a theory, as a physical theory. There are more inconsistencies that might come up when you're not exactly rigorous enough in your definitions. So they might seem some paradoxes. It might look like that there's a problem with the theory, but it's not the case. Just for if we define some of the things that we're working with in a more rigid form, we get rid of these problems. So my goal here is to present some of these problems. I'll be following closely a paper by François Giers that I'll link in the description later, and I'll present some of the problems that he shows there. I'll give some partial solutions after I present some of the math that we're going to need in order to discuss this, and then I'm going to show kind of how to solve these problems, and then we'll have some conclusion remarks and some discussion by the end. My goal here is not to present a functional analysis course, because a full-fledged functional analysis class, because first of all, I'm not competent enough to do such, and even if I were, there would be the lack of time, because it's a lot of stuff to talk about. So ironically, in some parts, this talk may seem a little bit hand-wavy, and some of the results, I'm just gonna claim some of the results, but that is my intention. So if anybody's more interested, you can go in the original paper that I'm referencing, and this talk is also an invitation for the Axiomatic Quantum Mechanics seminar that we're having. And some of these topics we're going to delve in more deeply in the upcoming seminars. All right, so let me start here with the problems. So the first problem, again in quotation marks, and let's discuss it a little bit. So the first thing, one of the first things that we see in a quantum mechanics course, more in a modern physics course, maybe, it's the Heisenberg's canonical commutation relation. So what I mean here, in quantum mechanics, one first learns if you open up a physics textbook, that your observables are represented by Hermitian operators. By operators, what a physicist understands by a operator is some kind of prescription that you apply to a physical state, and you can get information out of it. So in today's talk, we're going to work a lot with the position, which is the position operator, which is represented by the letter Q, and the momentum operator, which is represented by the letter P. What a physicist understands by these quantities is that you get a state, which in quantum mechanics we represent by a vector, which we call a cat. We write it down this way. This just tells you a physical state in which your particle lives, and then you apply an operator over it, for example, the operator P, and then you get information about the particle's momentum, for example. So this is the understanding that the physicist has, that the operator is kind of this magical way. You throw a particle inside some apparatus, and it spits out a number which you associate with the momentum. So in the canonical commutation relation, we have this commutator between the momentum and position operators, which results in a non-vanishing result. This is some authors take this as being an axiom of the theory. It's kind of like this is the path that you take from generalizing classical mechanics, because in classical mechanics, your observables commute. You know, your position and momentum operators, they commute with each other. If you drop that assumption that these quantities commute, you get a generalization, which is happens to be quantum mechanics. So in case someone is not familiar with these quantities, this is just the imaginary unit. And the h bar over here is called the Planck's constant, and it's a real number with units. It has units of angular momentum, and we work with it. It's a real small number, something like 10 to the minus 34, but it's a non-vanishing number. In the limit where h bar is 0, you get classical mechanics. All right, and the first thing that I want to mention is that our operators, we tend to represent them using matrices. And we want to talk about the most general way possible about these quantities. So this commutation relation, as it's written down here, is the way that I learned in my undergraduate course of quantum mechanics. The first thing that we might be a little bit careful, we might be a little bit, I don't know, too dull if we demand this, but the first thing that we might do is just put an identity operator here, just to make sure that we're talking about linear transformations in the strict sense of the word. And then in quantum mechanics, we will work a lot with these prescriptions for these operators. These prescriptions just say that for your state that we can write as a wave function, as a continuous differentiable function that represents the state of your particle, of your quantum object, we will write these operators using these forms. So when we apply the momentum operator, for example, what we are basically saying is that take the derivative with respect to x. We will be working in one dimension quantum mechanics, and then multiply by I over h bar. And the same thing for the position operator. You apply it to your wave function psi of x, and then what you get is you just put the argument dx outside multiplied by the wave function. So it's pretty simple stuff. Okay, so if we're talking about linear operators, one thing that we can do to work out, to understand a little bit of these operators, is take the trace of the operators. So first of all, in the left side of the equation here, we have a commutator, we have the product followed by a subtraction of operators. So if you take the trace, you can take the trace of this side, you know, as being the trace of PQ, which is just the trace of PQ minus QP. And you can show that when you take the trace of a product of linear operators, if they're the same dimension, you can commute them. So the trace of PQ is the same as the trace of QP. This means is that this side is actually equal to 0. However, if you take the trace on the right-hand side of the equation, the trace of h bar over I times the identity operator, this is clearly not 0. In fact, depending on the dimension you're working with, in the dimension of your problem, this is actually h bar over I times a n, which is the dimension you're working with. So what this result is telling us is that h bar over I is equal to 0. Which is inconsistent with the canonical commutation, because as I told you, h bar is not vanishing in quantum mechanics. So this is our first problem. All right. So I'll present all the problems first, and then we'll discuss some of the mathematics we need to in order to solve set problems. Okay. So, sorry. Okay, so the second problem I'll be presenting is this one, is as follows. So again, our operators, they're represented by these operations right here. So whenever you see a P an operator P, it means multiply by h bar over I, take the derivative. And then Q just means multiply by X. All right. So if you get a physics textbook, for example, Griffith's textbook, which is pretty much the standard quantum mechanics textbook for undergrads, you will find some phrase that says something along the lines of Q and P are Hermitian operators because they represent observables, which means that if they are Hermitian, that they're equal to their adjoints, which is the complex conjugate, the complex conjugate and transpose of the matrix that represents these operators. And if that condition is satisfied, you can guarantee that your operators turn out to have real eigenvalues, which are the values that you actually measure in a physical setting, in a lab or something. Okay, so if this condition, if this is true, if Q and P are Hermitian because they satisfy this condition, so then we have we can construct a new operator, which I called A, which is a combination of these two operators, and you can check that this guy is Hermitian. You know, you just write the dagger on top of the operator, and you remember that you have to remember that the sum of the complex conjugate, the complex conjugate of a sum of operators is the complex conjugate of each individual multiplied separately. So this would be PQ to the third Hermitian plus Q to the third P Hermitian. All right, and then in order to check this, you just remember that by the product of the adjoint of a product is the product of the adjoints after you exchange both the operators. So, for example, PQ Hermitian is just Q Hermitian, P Hermitian. And you use this to basically show that A dagger equals to A. Okay, you can check that if you want. So what this means is that if we write down the eigenvalue equation for some f that lives in the same space as the operator, for some function that lives in the same operator, the eigenvalues that you get must be real. Okay, however, if we take, for instance, a function, an f of x, which is a piecewise function that takes in the following form, x to the minus 3/2 times exponential of minus 1 over 4x squared for x different from 0, and then 0 if x is equal to 0. This function, first of all, we will discuss this a little bit later, but this is a function that is acceptable for this operation, because this function, in principle, that it lives in the same space as the operator A. They both live in a we will discuss this a little bit later, but they both live in a Hilbert space, which is the space of square integrable functions with a inner product, which we will define more further along the talk. So this function is square integrable. It means that if you take the integral from minus infinity to plus infinity of f of x modulus squared dx, in this case you actually get 1. We demand that the functions, they actually are finite. They don't necessarily have to be 1, but in quantum mechanics we will see later that we would like the functions to be equal to 1 when we take the integration on the real line, because it will have a physical interpretation later on. So this function is acceptable, but one can show that if you apply A to F, the eigenvalue that you actually get is h bar over I times f. H bar over I is clearly not real, so there is an inconsistency here again. Okay, so again, we have a problem. All right, that was the second problem. Now the third problem and final problem for today that we're gonna take a look. This I almost literally copied from Griffith's book on quantum mechanics. And it says that the operator is Hermitian if this condition is satisfied. This operation that we're doing here is what we will define later on as being the inner product of the operators. But for now, let's just take at face value that this is what we mean when an operator is Hermitian, that we can take the inner product and we can apply the operator A to the left side of your inner product, which basically is stating that if we take this definition as being the real one, what we're saying is that A is equal to A dagger. This is what this is what the treatment that we get in quantum mechanics textbook when we are defining what is a Hermitian operator. We're just saying that it is equal to its adjoint. All right. So if we translate this to a more operation like to form using integrals and stuff, we basically write this way. If we take our operator A to be the momentum operator and phi and psi as being wave functions that represent real particles, we have that live in a given interval. This is a common thing in physics. You know, we usually work with a lot of problems can be reduced to the infinite potential problem, in which your wave function lives in a given interval, and because of the potential well has walls whose potential goes to infinity, the wave function doesn't live outside that interval. That is how we constrain physically to constrain the wave function to live inside a interval. So leaving this interval as being 0 to 1, we have to satisfy some boundary conditions. The wave function in quantum mechanics, it has to be a continuous function and it has to be differentiable. It has to be actually smooth, if I'm not mistaken. I don't know if it has to be C infinity, but it has to be at least once differentiable. So given that, what we have to satisfy some boundary conditions. Which are that the wave function, it has to vanish on the limits of your interval. So it cannot exist outside this interval that you're given, because the potential is infinite for the case of infinite potential. So this is something that we have to satisfy. All right. So the way to check, the way to formally quotation marks to check if an operator is Hermitian in a physics textbook is by checking that the boundary term, if you do an integration by parts, vanishes. So what we want to obey this condition. If we put the right hand side of the equation to the left side, if we subtract both sides of the equation, we want, if the operator is Hermitian, this equation must be equal to 0. If we translate that to the integral form that I left it over here, this means that we have to have this condition, that this integral over here vanishes. Since the momentum operator is basically a derivative, you can do an integration by parts pretty easily. And when you evaluate the resulting condition in the boundary terms, in the boundary conditions that I've imposed here in this example, you get 0. So okay, the momentum operator is Hermitian as we just defined. Okay, so if by our definition, if the momentum operator is Hermitian, we have it represents observable, which means that it has real eigenvalues which you can measure in a lab. Okay, So it means that it obeys the eigenvalue equation. I'll just leave a little hat here on this P to indicate that it is the operator, and this guy over here, this little p here, is the eigenvalue, is the value that you actually measure in a lab. All right. So, but if we try to solve the differential equation, which underlines this relation, which means that we're just applying the operator p, which is a derivative, to a wave function, which you can take derivatives. You're going to get something along these lines, and this is a pretty simple differential equation. The solution are exponential functions. If we take the boundary condition of that psi 0 is equal to 0, which is something that we demand for the wave function to exist in the first place, we get that the total solution is 0. So no eigenvalues. However, if you take the spectrum, and by spectrum I mean the mathematical and physical spectrum, which are closely related, we see that the spectrum for the momentum operator is the whole complex plane. So something like sigma of p is equal to the complex plane. Which, first of all, it means that the momentum operator is not unobservable at all, because the spectrum is not the real numbers. The spectrum are not the real numbers. And second of all, we're going to see later that this function over here that we get as being our solution, our eigenfunction, if you will, this is not even part of the same Hilbert space as the momentum operator. So this is, there are a lot of problems here in this result. Okay, I'll just drink a little bit of water so we can continue with the math part of the talk. Okay, that being said, let's see some math. So again, my idea here is not to provide full, complete solutions to the problem that we had over here. The discussion is a lot more deeper than I'm going to do here. But what I intend to do is to show a little bit of what we are. How are we setting our theory to work in the first place, and where things are going a little bit wrong to get those results. Again, those results are not a problem with the theory itself. It's more about the problem with how do you approach the theory, how you work with the mathematics that underlies that theory. Okay, so the first thing that we need the arena of the game. We need to define where our physical states live. What is the space that defines the functions that represent our real observable particles? Okay, so what we require, the first thing that we require in quantum mechanics is this condition to be satisfied. This is commonly called Bourne's rule or Bourne's interpretation. What Bourne, the Bourne interpretation of quantum mechanics is that the wave function that represents a particle that represents a particle doesn't have any physical significance itself. What has a real significance is the modulus squared, which is related to the amplitude of the wave functions that represent probabilities. So quantum mechanics, you measure probabilities that you will find the particle in such a state, such and such state. And the idea that the modulus square of a wave function represents this probability of finding a particle in a given interval, for example, makes us impose this condition that the modulus squared of our wave functions must be normalizable, and they must equal to 1. The physical interpretation of this is that there is a probability of 1 for you to find the particle anywhere along the real line. In the case of 1 dimension, if you go to 3 dimensions, the particle exists somewhere. You can do you can make a stronger statement by demanding that in a given interval, in a given finite interval, the particle does exist in that interval. but it will be sufficient for us today to discuss the more the weaker case, that the particle exists somewhere in space. Okay, and in order to do that, our wave functions must be part of the space of square integrable functions, which I've represented here as L squared R dx. Okay, so if we equip such space with an inner product, with this inner product, we get the structure of a Hilbert space. Yeah, so the Hilbert space is basically a vector space in which you can construct an inner product which defines a metric inside your space, and with this same inner product you can construct, for example, a norm, so you can have the intuition about the size of the vectors that live in your space. And if you have a normed space, you have a Banach space. So basically, the every Hilbert space you can think of it as a Banach space, but the converse is not necessarily true. And the norm that you induce by this inner product is basically if you take the inner product of a function f with itself, a square integrable function, and then you're going to basically you can write this as this squared, which is just the modulus squared again of your wave function. So this is the kind of result that we want. We want to integrate this the modulus square and have it equal to 1. So the Hilbert space we're working with is the space of square integrable functions with this inner product that I've shown here, that where this guy over here is the complex conjugate of the function f, and we want our vectors in this space to be to have norm equal to 1, to have the norm equal to 1. All right. Just for completeness, we may also define a secondary Hilbert space, which is very common to work with in quantum mechanics and quantum field theory, which is the space of momenta that we say. The first Hilbert space that I've shown was the space of position, which your variable, the variable you're working with is the position variable, and we can define one in which your elements represent momentum, and the relationship, the way we take from one space, one Hilbert space to the other, is via a Fourier transform. And which is given right here. So just for completeness, this is something very standard in quantum mechanics. You're working in the space of position or space of momentum. All right. So now we define where we live, where the theory lives. Now we can start to talk about how we actually make measurements in this space. And the way we do so is using operators, the notion of operators that I've stated earlier. So actually, strictly speaking, the operator of on a Hilbert space is not just a prescription, as we are usually taught in a quantum mechanics course. It is actually a pair. It is the prescription, the linear map that takes you from that takes in the wave function, spits out some value, and there is actually a domain in which that operator is valid. So the operator is actually a prescription, so one, a prescription, a rule, if you will, and a domain given by dA. And the idea behind the domain is that it is a dense subspace from the Hilbert space. And I'm not going to get into much detail on what that means, because this will not, the fact that we have that the operator is not just the prescription, but it's actually the prescription plus a domain, will already help us to solve the problems that I stated earlier. And it is pretty natural to think about the operator as being both a prescription and a domain. When we're taking a calculus course, we are always, when we're working with functions on the real line or in the Euclidean space, we are always worried about not just the prescription of the function, but also where the function actually, you can work with the function, where it actually works. So if you have a function that goes something like something, I don't know, an f of x that goes like 1 over x, probably you won't want the, making this a little bit more general, proportional to 1 over x. We'll probably not want the x to be equal to 0 to be in your domain of your function. You know, that's a little bit problematic. The same thing happens here when we're talking about Hilbert spaces and operators in such space. We want to not only the prescription, the formula, the way we use the operator, but we also want to know where the operator lives. Where the operator works. It lives in a Hilbert space and it works inside a subspace of that Hilbert space. Okay. Just a remark. For two operators to be equal, and this is something very important. For we to define two operators A and B to be equal, they have to both have the same prescription. We can only write this statement over here that the operator A is equal to B if both the prescription of them is the same for a given function that lives inside the domain of these operators, and the domain of the operators must coincide. Okay, this is something very important. Most in quantum mechanics, we just see this first condition being satisfied. The books, the textbooks, they always show the operators, they are the same if they act the same way on a given function. That is not always true. You have to check both the prescription and the domain of your operators. Okay, so a couple of examples here. Again, working with our position and momentum operators, which we will work on them during the talk. So again, well, the way we define the action of these operators, the prescription of them is for the position operator, we just multiply by x, and then the momentum operator, we just take the derivative. Okay. So we can define the domain in which you define the operators is not unique. It will physically thinking. If you think on a more of the physical side of things, if you design an experiment to measure the position of a particle, which takes place in a lab, in a one-dimension line, for example, that has a length of a meter, the space, the domain of the operator, the possible, the way this operator works is going to be different from when you make the same measurement. If you make a measurement of a position of a particle inside the LHC, for example. So for different experiments, the operators, they accept different domains. For different experiments, there are different domains for the operators. So in particular, we can define the maximum domain of each of these operators. That being said, what I mean by a maximum domain is the maximum domain in which you can measure and you can take for any experiment, and you're going to be able to measure the position of the particle. So for the case of the position operator, the condition is this one. You must have that the operator multiplied by the state you're working with lives inside the same Hilbert space. This is the same thing as saying that for a given square integrable function, the value of x squared, this polynomial x, the position, squared times the modulus squared of your function must also be square integrable, must also be finite. Okay, and this something similar happens for the momentum operator, in which the condition is that when you plug in the derivative and the h bar over I inside the modulus squared on your inner product, the condition that you get is that the derivative must also be square integrable. So by this over here, I mean derivative. Okay. It is helpful though if you want to work out with both. So first of all, if we take a close look at these domains, both the maximal domain of the momentum operator and the maximal domain for the position operator, we see that they are not exactly the same. You see the domain for the momentum operator is the subspace in which both the function and its derivative are square integral, and the maximal domain for the position is the subspace of the Hilbert space in which both the function and the function times x squared times x actually is square integrable. So they're not necessarily the same domain. So it is pretty much pretty useful if we define a space in which both of the operators can be worked upon, and we're not going to have any more problems with that. And that motivates us to use short spaces to define these operators. Short spaces, they are defined as being the space of functions that decrease more rapidly than any inverse of a polynomial, i.e., that means that if you take, the supremum for an x belong to R of the modulus of a polynomial x to the beta times the derivative of the function, this must be finite. Okay, and so this is the space for the short space. Short space is enough for most of measurements in quantum mechanics. So well, given a small spoiler for the end of the talk, deep down what we're doing in quantum mechanics, when we're not considering the different domains for different operators, we're just assuming that they are valid in a short space, that the domain of the operators we're working with are short spaces, because they're pretty easy to handle, and both the position and the momentum are defined. The short space is a valid domain for the position and momentum operators. And there's also a very good thing about short spaces, that they are invariant. They are invariant under the action of the operators. Which means that if I take my position operator, which whose domain, a valid domain for it, is the short space, I can do any operation using the position space. I can multiply by itself 100 billion times, and the domain in which this resulting operator is valid is still the short space. And the same thing goes for the momentum operator. So this is a good thing to use whenever you're working with both the position and the position operator and the momentum operator. If you want a domain in which both of them are valid, choose your short space. Okay. Another definition that we're gonna have to use to solve the aforementioned problems is the definition of adjoint for a joint operator, which I already mentioned it. I said the word adjoint a couple of times during this talk, but now we define exactly what I mean by that. So we define rigorously the adjoint as being the operator, this operator A dagger for which you define a domain which constitutes of any phi tilde, which satisfies this condition over here. So for every psi that we have in the domain of our operator A, we can always find a phi tilde that lives in the same Hilbert space in which this condition is satisfied, i.e. the action of the operator A dagger over a state phi results in another function that lives inside the same Hilbert space that we were talking about before. So how do we know if the adjoint, at least the prescription of the adjoint is the same as the operator? I.e., in the physics context, we would say that A was equal to A dagger whenever the prescription, whenever the action of the operator, both of the operators was the same. So the way we do to check that is by doing the integration by parts method that I alluded earlier. So remark, if the surface term in the integration vanishes, then A and A dagger have the same prescription. All right, so let's test this. Let's try to work this with some of the examples that we are already seeing during this talk. So if we have again a particle that lives in the interval, the closed interval 0 to 1, we define the domain of the momentum operator as being both the condition that the derivative of the function lives in the same Hilbert space, as we talked about earlier, but we also have to impose the boundary conditions because the wave function has to be continuous, as I mentioned in the beginning of the talk. So both of these conditions have to be satisfied in this problem. So you can see that for this specific problem in which we're imposing a condition where the particle can live, we have a slightly different domain as the domain for the momentum operator that we talked about earlier, the maximum domain. Okay, so if we take the previous definition of the domain for the adjoint, if we copy and paste it and just exchange A for P, we get this domain over here. So we want to know how P dagger acts, how the adjoint acts. If it acts the same way as the momentum operator that we saw earlier. So to do that, we have to verify that what result we get when we do the integration by parts method that I talked about earlier. So if you substitute, if you do the integration here by parts, if you substitute P for H bar over I times the derivative, as I defined earlier, taking good care about where you have complex conjugate quantities and all that. If you do this integration, you're going to find these terms again, which were the same as the problem that I showed in the beginning, and it is equal to 0. So what we conclude from this calculation is that, number one, P and P dagger have the same prescription, i.e., if you apply the adjoint of the momentum to a given state, you get H bar over I times d dx of psi. It is the same. It acts the same way. However, if we take a closer look, we can see that the adjoint doesn't need the same the same boundary conditions that as we stated earlier for the domain of your momentum operator, because when we do the integration by parts over here, this condition is already satisfied. So for one domain, we already defined the condition that the function vanishes in the boundaries of your interval, and here for the domain of the adjoint operator, we do not need this condition because it is already satisfied. So what we get is that the domain of P dagger can be actually written as the set of functions that live in the Hilbert space, such that the derivative also lives in the Hilbert space. So this is the same as the maximum domain for the momentum operator that we talked about earlier, but this is not the same domain for the momentum operator we're working in this particular problem. So just for clarity, the other one we were saying that we wanted a functions that live in the Hilbert space such that the derivative lived in the Hilbert space and the function vanishes for these values. So you can see that the momentum, the domain for the momentum operator is a lot more restricted than the domain for the complex conjugate, for the adjoint operator. So they are not the same domain. So this is going to turn out to be pretty useful for us when we work the problems that I showed. So a definition inspired by that is that an operator is Hermitian if the prescription of both it and its of both the operator and its adjoint is the same. However, we define that an operator is self-adjoint if the operator is equal to its adjoint, which means that both this is satisfied and the domains are the same. So when we see in a physics textbook that we take Hermitian operators and self-adjoint operators as being synonymous definition of one another, that is not true. The Hermitian definition is a lot more general. It doesn't take into account the domain of the operators. It just takes into account the prescription, how the operator actually operates over your given state. And the definition of a self-adjoint is a lot stronger. You both have the prescription and the domains are the same. So this is something that we have to take care of. And there's something there. If you study, there are some theorems. I forgot the names of the theorems, but you can show that if an operator is self-adjoint, this means that it has real eigenvalues. For Hermitian operators, that is not necessarily true. So the condition in which you can guarantee that your operator is going to turn out to have real eigenvalues is if that operator is self-adjoint. And in particular, the momentum operator is Hermitian, but it is not self-adjoint. So this is a very important thing for us to understand, that when we're talking about, when we're constructing our physical theory, our quantum mechanics, we want to construct operators. We want to use operators to represent the observables that we have in nature, and these operators, they must be self-adjoint, not Hermitian. They're not synonymous. So that is how we actually end up constructing our theories, by taking the observables to be self-adjoint, not just Hermitian. Okay, so now how to solve the problems with all of these these tools that I've talked about. We can pretty much at least see where the problem is going bad, what is the problem with each of these problems that I've shown. So the first of the problems was what we had was, we were taking a trace of something that is not a trace that is not, that doesn't vanish, and we were saying that it was equal to something whose trace is equal to 0. You know, so we had a little problem over here. The relation, the Heisenberg commutation relation, is something intrinsic of quantum mechanics. So the thing is that this condition is strong enough for you to actually construct your theory in a infinite dimension Hilbert space. This means that quantum mechanics is realized over a infinite dimension Hilbert space, which is, you know, calligraph H. So this is the condition. The trace, when we're taking the trace of a operator, we're assuming that these operators are finite dimensional. So if we take the quantum mechanics to be formulated on an infinite dimension Hilbert space, the operation of taking the trace doesn't make any sense anymore. So this equation doesn't make any sense. You cannot write that down. So the commutation relation still holds this equation, and there's actually there are some caveats on this, because, you know, since the momentum and position operators are not exactly finite, they're not exactly this way. You cannot exactly write commutation relations, but this is something beyond the scope of this talk. Another argument that you can state is that the momentum and position operators, they're not bounded operators. What I mean by bounded is that if you take the norm of a operator A, F, there exists some number in which a number greater or equal to 0, in which you limit the action of your operator inside your Hilbert space. This is not satisfied for the momentum and position operators. So when you do that, you cannot even write exactly these commutation relation that I've wrote here. But this is, again, this is way beyond the scope. The thing is that this condition over here is sufficient for us to want to formulate our quantum mechanics, our theory, in an infinite dimension Hilbert space. That is the idea I want to convey for today. The second problem that we had was, we defined a operator which we claim to be Hermitian, because it was composed of Hermitian operators, and because it is a Hermitian operator, it has real eigenvalues, and it turned out that for a given function, we didn't have a real eigenvalue. We had an imaginary one. So how do we work this problem out? So the first thing is that what we're doing here in secrecy is that we're working with these operators, considering their domains to be the Schwartz space. So we're considering it over here that the domain of Q is equal to the domain of P, which is equal to the Schwartz space of rapidly decreasing functions. The thing is that for us to work in this operator, in this subspace, I mean, the function that we're defining, that we're applying our operator, must also be a rapidly decreasing function, which this function is not. This function does not decrease, in particular if you take x to the third of f, of the derivative of f, you can see that that condition of the supreme is not satisfied. Because the problem arises when you have you know, this division by x over here and this modulus here, which goes with a negative exponent. So this is not finite. This function does not, when you multiply by a polynomial, it's not bounded anymore. So this function is not even is not part of the same, is not included in the domain in which your operator is defined. So one could work with this function if you consider, for example, the domains of the maximum domains of the position and momentum operators separately. But once you put them together, you want to work with a domain in which both of them are valid. In this case, it turns out to be the Schwartz space. And the function is not defined in the Schwartz space, so you cannot do this operation at all. So there's that. And the last problem that we had was that we were saying that the momentum was a Hermitian operator, and therefore it was observable. But we know from functional analysis that the spectrum of the momentum operator is the whole complex plane. And we also saw that if we apply the momentum operator to the wave function, we get this result. And you can check that this function over here is not square integrable. You know, if you multiply by the modulus squared, you're going to get an x. You're going to get the integral of dx evaluated on plus and minus infinity that is not bounded. And so this guy is not even in the same Hilbert space as the momentum operator. So, but the thing the first mistake that we did was by assuming that if P was Hermitian, that this implied that it was unobservable, which is not. If P was self-adjoint, then you can guarantee that you have real eigenvalues, that you have unobservable. So if P were self-adjoint, then it would be observable. And some of you might be asking, but I can measure the momentum of my particle. This is absurd. How can you state that the operator P is not unobservable? I can make a measurement. The truth is that there are a lot of caveats that I'm skipping over here. You can define the action of the operator using Weil series, if I'm not mistaken, and you can actually get some physical sense of the momentum operator. But the momentum operator, in the way we defined it in quantum mechanics, with the maximum domain, doesn't represent its eigenfunction, the function that result of the action of this operator. Its proper functions are not observable itself. So what you observe in the lab most of the times are expected values for momentum operators, not the momentum eigenvalues themselves. So there are some caveats on this, but you can start by just showing that the assumption that just because a operator is Hermitian, it is observable is wrong. If the domains of P and P dagger coincided, you could make such a statement. All right, we reached the end of the talk. I just want leave some conclusions, some random thoughts that I have about this subject. As of course, these thoughts are more biased since I am a physics undergrad. But and I hope that some of these points will start a discussion later on. So the first thing in the mathematics sense is that the domain of the operators that we were working are very important, but they're usually neglected in physics textbooks. So just by the fact that we take the domain in consideration, we can already work out some of the problems that we were having. If we let the too little math from, if we don't show a lot of the math, if we keep treating Hilbert spaces as being this big black box in a undergrad quantum mechanics course, it may open a room for confusion, for statements, for problems like these ones. These are pretty simple problems. If you take a look in the paper that I mentioned, there are other problems that open up when you don't take the domains in consideration, if you're not very rigorous. But if you put too much math in a quantum mechanics course, you alienate the students, especially those students that are more experimentally inclined. So I'm a strong believer that there's always room for middle ground, for working, not putting too much math as to make the course too dense. But I also believe that you can put a little bit more than what is already taught nowadays. So that being said, I thank you all for the attention. This was I said everything I wanted to talk about, and now I open up for some discussion if anybody is interested. So thank you.
Ok. Aí a discussão vai ser em português. Eu queria agradecer. Apresentação muito boa. Eu achei assim.
Obrigado.
Eu fiquei com. Eu tô um pouco. Eu vou mandar. Eu achei muito bom, principalmente pra galera do seminário, sabe? Eu queria que tivesse mais gente aqui. Eu vou mandar lá o vídeo pra eles depois. Porque, sabe, você conectou com o que a gente vê lá em mecânica quântica. Você começa com a funçãozinha de onda lá. Tal. Eu acho que isso é importante.
Eu tô ouvindo você, só vou botar aqui pra carregar meu computador, que tá ficando sem